So it's my great pleasure to introduce our today's speaker, Simpson from University of Nice and IS. He'll be speaking about constructing buildings, harmonic matrix buildings and WKB problem.
Okay, thank you very much. It's a great pleasure to be here. Thanks very much for the invitation. What I'd like to talk about today is joint work, recent joint work with Katzarkov, Alex Noll and Pandit. So for some of our motivation were the recent theory of spectral networks. This was kind of our main motivation. The theory of spectral networks of Gaiotto, Neitzke. And there's a question, well, I'm not going to be discussing this question, but this is really a motivational thing, which is the relationship with the theory of stability of moduli spaces of stability conditions. So, let me just put some people, Birchall and Smith kind of have one of the first main works about this. The conjectural wall crossing is kind of an integral part of this whole theory. And
what is this stuff all about?
Well, I'm not going to talk too much about it.
It's engineering, stability.
Yeah, but maybe we'll try to see a little bit about what's going on. We'll try to see a little about what's going on here. A more recent version of the Birchall and Smith work by Fabian Heiden with Katzarkov and Davidge. And then, so we really applied, just to sort of get the references out of the way here, we really applied the recent theory of Parreau, which is a generalization of the Morgan-Shalen compactification. Okay, so that's kind of all the stuff that goes into what I'd like to say here. So to start off with, let me just start from a point which is a little bit comes a little bit from the talk of yesterday, but this should I'll try to explain it in a way which doesn't refer to yesterday's talk. So it's like X be a Riemann surface. And today we're going to actually think of X as being simply connected, or so. We'll think of that as having, we might have started with a compact Riemann surface, but then we took the universal cover, okay. And then let's look at a WKB problem. So we have a vector bundle V. Now, since we've gone to the universal cover, which is just a disk, we can actually assume that it's trivial. And we have a family of connections. And let's think of this, so we'd like to think of this as a family of connections of the following form. Nabla 0 plus t times phi. So Nabla 0 could very well be just the trivial connection. L0 is just D for sections of our bundle. And phi is a matrix. It's just a matrix of one forms, okay? And that's what's in terms of yesterday's discussion. So phi here, phi is a Higgs field. Okay, now our connection just gives us a system of ODEs. Okay, so nabla t of f equals 0. Is a system of ODEs, which we can write in the following. We could just write explicitly, just df. So f is a column vector. dfi dx plus t times summation pij of x times fj equals 0. Okay. So this is just a system of first order ODE.
Is x a real or a complex coordinate on your Riemann surface?
X is a complex coordinate. Yeah. So here x.
So phi is of type 1, 0.
Yeah. So
Are the entries holomorphic or they're
yeah, the entries are holomorphic. So here we have a first order ODE, which depends on the parameter t. And the WKB problem is to understand the solutions as t approaches infinity, as t gets big. Okay. So we just have a system of ODEs and some coefficients are getting big. We'd like to understand what is the solution look like.
K is for Kramer's?
Yeah, what's the way you want on Kramer? I don't know who decided the order of it. Anyway, I mean, alphabetical order would be BKW, right?
There's something else in physics that's the WKB.
Well, this is the same, yeah, this is the same thing. So let me just write down an example here. So the example which I'll be discussing a little bit more, it's a third order, would be just 1 over t cubed times d cubed f dx cubed minus 1 over t df dx plus x times f equals 0. Okay.
Do you know some bounded, so you know that you could solve this all the way to infinity?
Yeah. I'll say in a minute the basic bound on the solution. Just for comparison, a typical second order equation is going to be something like d squared f 1 over t squared d squared f dx squared plus v of x times f equals 0. And this is just Schrodinger's equation. There's one variable. Just Schrodinger's equation and like t is like 1 over h bar. So that's so as you say, when you say the physicist approximation, the physicists are not interested not in fact in the limit as t goes to infinity, but just when t is really big, which is to say 1 over Planck's constant. But here we're actually going to look at the the behavior as t goes to infinity. And these guys are let me just write down here, for example, this higher order equation for a function, I will just recall, is equivalent to a matrix equation if we just let phi, for this example, be, say, the matrix 0, 1, 0. I went through the first one, but we have 2 more. So yeah, so if we just higher order equation for a function, which may be a more comfortable notation for some people. It's just the same as a vector equation by using this companion matrix thing. And the vectors, the fj's are just the successive derivatives of the function. Now, this is actually an interesting form to put this in because it suggests immediately what's going to happen next, which is we can take the spectral curve of phi. So this is a curve sigma inside the cotangent bundle of x. So sigma is the set of points x, comma, y times dx, where y is an eigenvalue of the matrix Vij. Okay. And in our example here, if you do a matrix like that, then the characteristic polynomial of the matrix is just given by the last row, and it's just the same. So sigma is just given by y cubed minus y plus x equals 0. So now let's think of that as, let's see, something like that, I think. If I'm not mistaken. And I guess x equals y minus y cubed.
You have 2 non-zero terms there, and 3 non-zero terms there. Oh, they come from the diagonal. Oh, yeah, right. No, but I mean the characteristic polynomial. See, they're the terms on the diagonal.
Yeah.
Okay, sorry.
So, I mean, roughly speaking, we just take our system of equations and replace the derivatives by a momentum variable, basically.
Simple.
The simple way, something like that. Okay, so sigma looks something, in this example, looks something like that. We have 2 ramification points here, and at some other point, there's going to be 3 solutions. Okay, so let's let phi1, let's let phi dot be this triple of solutions phi1, phi2, phi3, where phi I is equal to yi dx. So the phi's are forms rather than functions, and the yi's are the solutions. So that's to say that in more invariant terms, the phi's are the eigenforms of this matrix. So that's called the spectral curve. And it's kind of the thing which is controlling this WKB problem. Let me just over here mention that in this case we're going to have phi dot equals, in this rank 2 case, phi dot is just phi1, phi2, with phi are plus or minus the square root of dx. And in this case, if we take v times dx squared, this is what's called a quadratic differential. So I mean, for those people who have heard of the theory of quadratic differentials, what we're doing here in the higher rank case is just, this spectral curve is just the generalization to higher order differential equations of this notion of quadratic differential. So now we'd like to understand the solutions. So let's let T PQ, and it depends on T. Let TPQ be the transport matrix of solutions. So that means that if we take the solution vector at the point Q is just the matrix TPQ times the solution vector at the point P. Okay? You know, since it's an ODE for any fixed value of T, there exists a unique solution. If we start with a solution at the point P, there exists a unique solution to the point Q. Remember that we're assuming that X is equal to its universal cover. X is simply connected, under those notations, there's a unique path up to homotopy from the point P to the point Q. Otherwise, I should include the path inside this notation. Then let's define the exponent. A number of people tell me that this is called the Lyapunov Exponent. Like, roughly speaking, I think that's correct notation. Mu PQ, so let me put it superscript sup here. Well, sorry, I did something in that order, but let's just take the lim sup as t goes to infinity of 1 over t times the log of the size of the matrix, with the following observations. So one is that t here now we restrict to a real array. So a priori up till now t was a complex variable, but it turns out that the behavior of the solutions depends on the direction in the complex plane that you go. So we actually, to study the solutions more precisely, we need to fix a direction. If you change the direction of the ray, that just amounts to multiplying phi by some complex number of norm 1. Okay? If we just rotate phi, that's the same as rotating t. That's the first observation. And the second observation, which I probably should have said before, is that we have a basic estimate on ODEs says that the size of the solution matrix is going to be bounded by, say, 1 constant times e to some other constant times t. It just says that you can solve a system of ODEs, and this is for a fixed but what we're doing here is we're fixing the points p and q and looking at t going to infinity. You could also, it's also an interesting question to let the points go to infinity too, but that's not being discussed today.
That depends on the fact that matrix depends linearly on the coordinate.
Yeah.
Are they all going to depend linearly on the coordinate, your examples? I mean, this one it is.
They're just linear systems of ODEs. So remember, the system is just df I dx plus t times phi I j of x f j.
The domain.
So this is just matrix multiplication. So that's a linear function of f. So we're not doing a nonlinear equation in terms of f. So just a linear. It's just the easiest possible kind of ODE. Okay.
It's on f.
X. For f. So this is completely the easiest possible kind of ODE. Okay. But still we don't really understand very well what happened. So the basic estimate on ODEs is that the size of the solution is just bounded by some exponential times the size of the coefficient. Okay, so that means that this lim sup exists. Right, these numbers are all bounded by C2 basically. And the question is, what's the best exponent? Now, so now I'd like to apply the theory of Parreau. The theory of Parreau says that, okay, we don't really want to look at this lim sup because we don't know how to calculate that. So let's try to actually have a limit. But if you try to make a limit, then you're not sure whether the limit exists because the thing could oscillate. So you fix, so that's sort of the basic motivation, I think, for choosing an ultrafilter. So you choose an ultrafilter omega, which, to be precise, let's say supported on a sequence ti going to infinity, and really omega is just a point in the Stone check compactification of n. So we could also, I mean, you could also take the Stone check compactification of the full positive real line, and t is taken off, because on Wikipedia it said that Stone check was actually essentially known by Tikhonov earlier. So choose an ultrafilter, and then basically, what's an ultrafilter? It's just a way of taking the limit of a subsequence whenever you need to. Okay. So it kind of makes all limits defined, basically. Limits of bounded things are defined. That's just the universal property of the compactification. So then we can define the ultrafilter exponent.
Raise the stakes of logic now.
Sort of, but it's kind of a natural thing to do, actually. For the more number theoretically inclined, what we're really going to be trying to do is we're really going to be trying to look at a valued field. But we're thinking of functions of the variable t. So if you'd like to think of a valued field of functions of the variable t, and the valuation is this exponential growth factor, basically. The only thing is that functions of t are not going to be a field because they might have lots of zeros or something. So replacing the notion of valued field in Broussard buildings for valued fields and stuff like that is this theory where you choose an ultrafilter. Okay, so then we can just define the ultrafilter exponent, and then Parreau's theory tells us that there exists a map to a building. So it's a little bit of a weird building. It's an R building.
What's that word you wrote with a T? I can't read it. What's that?
Parreau and Parreau,
Oh.
a student of Frederick Poulin. And I should also say using Kleiner and Lee. And generalizing Morgan-Shalen. I think the ideas are kind of due to Gromov and Thurston, actually. It's this idea, I mean, those of you who have, some of you may have heard, Thurston say, oh, you just take the disk and kind of look at it from really close up and it starts to look like a tree, basically.
Right.
That's what's going on here. So we're just taking a symmetric space, a higher rank symmetric space, and rescaling the metric. And the point is you got a limiting R building. So in those terms, it's kind of equal to the Gromov limit of the symmetric space SLRC on SUR with 1 over dt times the distance.
Mod what?
SUR.
SU?
Yeah.
Okay. Oh, yeah.
And this is a G mod K. So this is some symmetric space with a negatively curved symmetric space. And we take the metric, but we rescale the metric. And then we take some kind of limit of that guy. So the point is there's a building and a map.
The parameter is going to 0 or infinity. That parameter. I can't read it. It's going to.
This is 1 over t, so that's going to 0 as t is going to infinity.
Well, is that what you want to do?
I think so, because that means that, so points that are at finite distance in this guy correspond to sequences of points that are very far away inside the symmetric space. getting big inside this metric space. But then we're sort of rescaling distance down to say it's a. So I mean, does it mean we're looking at it from far away or from close up? I guess maybe more far away actually. But
I think this intuition of Thurston is, if you look at it from far away, you make the curvature very negative, then it looks like a tree.
yeah.
That's the intuition. Not very near zero, but then it looks like Euclidean.
Yeah, I mean, maybe it's I guess far away. Probably better.
Yeah.
Okay,
I think it's good. I think
but I mean, it's not the little
it's
disk that's spreading off into the horizon. I mean, it's the full non-compact. I mean, it's the full complete hyperbolic space. It's going off to infinity. That's the guy that you're looking at far away.
When you scale down something, the curvature goes up. So that's what he's doing. It's like a very small sphere has a very
Oh, it
large
does?
arc.
Oh, okay.
A very small sphere has huge curvature. It's the same thing, but this is negative curve.
Okay.
I guess so.
I want to make the curvature get large.
Yeah, that's what he's doing.
That's okay.
And so, but then there's some directions in which it stays flat. Those are like given by maximal tori in the group, basically. So anyway, so you get this R building, so the point is we have a map from X into this building, which exactly does what we want, which is to say that this the exponent defined in its ultrafilter way. This whole thing is all limit using the same ultrafilter. Okay. This is going to be the distance in the cone, but here I have to put an F here. It's like a Finsler distance in the cone from H of B to H of Q. Okay. So this tells us that we have, so we lost a little bit of information here because we had to choose an ultrafilter, so we took a limit here instead of a lim sup. Okay. But you can imagine, I mean, for a given case, you might have taken an ultrafilter which actually calculated the lim sup.
This gives you a locally compact space or something?
Well, it's not really locally compact. It's an R building. So it's like it has. I mean, in the case of an R tree, it has like
There's many trees.
there's little branches
Like an
coming out
R
all the
tree.
time. Yeah, it's like an R tree. Yeah. So we lost a little bit with that. I mean, so we lost the structure of our space is kind of bad, and we have this choice of ultrafilter here. But on the other hand, now we have a sort of a space. X is mapping into a space which is controlling our exponent. Okay. Now, so now our basic one of our basic results here is the differential of this map. So this map is locally harmonic, in particular continuous. But that's this estimate here. I mean, what did I say? This estimate here, if you understand that when P is very close to Q, then this C2 becomes close to 0. That's going to tell you that it's continuous, actually.
It's locally what?
So it's locally harmonic.
What does that mean?
It's just that picture you drew at one of those meetings. You have a point and a bunch of things sticking out, and the average of them is equal to the value.
Exactly.
We need a measure, though. A measure?
Well, actually, well, we have a measure on here. Okay, I mean, we'll have some kind of we have metric structure on here. We don't actually need a measure on X because it's a two-dimensional surface. So the harmonicity condition.
No, I'm not worried about X. I'm worried about over there. Talk about harmonic.
Well, this is a building, but I'll say a little bit more about that, especially in the rank 3 in the SL3 case. It's a building which is modeled on a specific. It's modeled on the affine space that's the same one as the Bruatitz building for the group in question. For example, SL3. I'm going to say that in a minute. Okay. And so this guy, I mean, each of the apartments has a nice Euclidean structure.
So you have a vast number of reasonable things.
Yeah, well, let me just say a little bit more about this, but let me just finish the statement. It's locally harmonic with differential dH is equal to the real part of this phi dot thing. So, in this statement, we'll just take a definition here that this means that any.
But if you can prove that equation, it means it's something that looks harmonic, right? Phi is holomorphic.
Yeah.
Huh?
Yeah, exactly.
So if you prove that equation.
Well, we're just proving that equation. We're not.
Ask.
Okay.
I don't know what it means, so it's Phi a function.
Well, I just wanted to say, but what we want to say is that any point x in x except a branch point of the spectral curve has a neighborhood ux such that h takes ux into an apartment.
Oh. It's locally a harmonic map, right?
It's locally a harmonic
Not a
map
map harmonic
into
function.
an apartment.
It's going into a nonlinear object.
Oh, no.
That's right.
No, but it's not. This statement is it's actually going to a linear piece of the nonlinear object.
And it's
But
harmonic
any
in
point-
any classical way.
Any point has a neighborhood such that this goes into just an apartment, which is just an R minus 1. Right, this building is built up out of these apartments, which are affine spaces, just real affine spaces. And the part of the harmonicity condition. So that was sort of shown by Gromov when they, and maybe Korovar shown when they did the general theory of harmonic mapping into buildings and stuff like that. They actually proved that if you have a harmonic mapping in terms of energy minimizing, then it has to have this property. But we're just proving this property back in directly.
So what is phi dot? Is it maximal eigenvalue?
Yeah, so phi dot is my notation for the tuple phi1, phi2
All of ours.
R. Since we're talking about SLR representations, the sum of these guys is 0. So let me just get to that. So
it might help to say that, harmonic map into Euclidean space is just a vector value function where every component is a harmonic function.
yeah. And I said locally harmonic here because Richard Wentworth pointed out to me that actually these maps that we're talking about here could be locally harmonic. They might not actually be globally energy minimizing. So there's something which I don't understand very well about that. But this is just.
Can't you turn a corner in an apartment and go into another apartment and at the corner point would make sense?
Part of the statement here is that this map, you can go like that. You can go from here into here. Yeah. But that counts as an apartment. There's an apartment that goes
So you can
like
flatten
that.
it out.
But a part of the statement is that you're not allowed to turn around in the same apartment.
Yeah,
So
that's the main thing.
So we're not sort of reversing ourselves inside a given apartment. So the map is not actually folding. So let's just look at the case SL2. The case SL2, then the standard apartment is just R. This cone omega is an R tree. And this phi dot is just plus or minus the square root of b. In the example I was talking about, this is just the square root of a quadratic differential. Okay. And this says that d. This says that it says that it says that we have a map from x into this tree. And the differential is given by the quadratic differential. So if you think about it a little bit, if you're looking at maps from something into a tree that are harmonic in this sense, so their derivative locally is a holomorphic form. That holomorphic form is well defined up to a sign change, because inside a tree you don't have necessarily a uniquely defined direction at any point. So your direction might be positive or negative. So the differential is well defined up to plus or minus 1. That's why its square is a quadratic differential, which is well defined. Okay. Now in the case of SL3, A is R2. Well, let's write that as the set of x1, x2, x3. Well, no, it's like this should be called z1, z2, z3, I guess. Our standard department, we should actually think of it as a space of triples of function points in R3, but whose sum equals 0. Okay, so that's an R2. The Finsler distance from x1, x2, z1, z2, z3 to z1 prime, z2 prime, z3 prime is defined to be just the mass over I of zi prime minus zi. Okay. So it's non-symmetric, in fact. I know this max is always positive because the sum equals 0. Since the sum equals 0, the sum of the differences equals 0. So we have three numbers whose sum equals 0, and we're taking the max, so it has to be positive. Okay.
So if you interchange the primes,
If we exactly
the max will change, right?
right, but in fact, if we take df from z to z prime and df from z prime to z, these determine the position of z prime minus z up to the Weyl group. So there's an action of the permutation group. And up to the action of the permutation group, I mean, in terms of Weyl group, you can sort of move any vector into the maximal Weyl chamber. And the position inside there is going to be determined by these two numbers. That's in the SL3 case. In the higher rank case, you have to think of taking sort of a vector distance, which is actually just, it's better to think of the vector distance as really being the value inside that maximal Weyl chamber. But what we can say next is only for SL3 anyway. So. And so what we're just saying here in this SL3 case is just that 8 locally H is just given by coordinates z1, z2, z3. Such that d of these zi's are just the real part of and so remember that so the choice of coordinates here is not really well defined on in the building. The building is that when you're piecing together the building, you have this action of the symmetric group. So the choice of the three coordinates themselves is only defined up to permutation, and similarly, the choice of these three spectral differentials was also only defined up to permutation. So that's why it sort of makes sense to say d of a map to a building is equal to the real part of some differential coming from a spectral curve. Right? Those are both sides of things which are well defined up to action of the symmetric group. So okay, so that tells us something. In the case of trees, so in the SL2 case, what happens? In the SL2 case, everything's pretty nice. So if phi is generic, like not even the matrix phi, that's just this phi dot in the spectral curve. If phi dot is generic, that really means we're talking about this quadratic differential. Then we can define a tree T phi is the space of leaves of the foliation, of the measured foliation. Which corresponds to this quadratic differential. Or if you like, just the foliation defined by the condition d phi equal, a real part of phi equals 0. Right, in the SL2 case, these phi's are well defined up to plus or minus. So real part of those guys equals 0. That defines a nicely defined foliation on our image. We can just take the space of leaves of this foliation, and we have a map which I'll call H phi. So we have a map like that, which is defined just in terms of phi. But furthermore, the condition here that I was saying, where we're not allowed to fold things, tells us that for any other map to a tree, for any other phi harmonic map to a tree, there exists a factorization. And also F is an isometry. So the conclusion, the corollary, is that the ultrafilter exponent is just also the distance, the Finsler distance. For a tree, the Finsler distance or the non-Finsler distance are the same. It's just the distance in the tree cone omega from h phi, the distance inside the tree t phi from h phi of p, h phi of q. Another way of saying that, it's just the measure, it's just the distance from the point p to the q transverse to this foliation. In particular, it's independent of omega, so the limit exists. So
which case are you doing now?
now this is the case of a tree. So this is the case of SL2. Case of a tree, and we're also assuming genericity.
And where's the foliation?
The foliation is the foliation defined by this quadratic differential. The foliation defined by
On the surface.
on the surface. Yeah.
Okay.
Yeah.
Oh, yeah.
So we, in this case, we just get an estimate for the exponent. So what we'd like to do is the same thing in the higher rank case. So, but let me just say in terms of motivation. So it became apparent, we were discussing with Ludmil and his students and postdocs and everybody, and we were discussing this whole Bridgeland-Smith space of stability conditions and stuff like that. And at some point it became apparent that one of the key phenomena that was happening for the SL2 case, the Bridgeland-Smith papers for the SL2 case, for example, one of the key phenomena that was happening was that you had to sort of, the geometry of this tree here was kind of coming into play, basically. So we decided, okay, let's try to generalize that to a higher, to a higher range.
Interesting cases for SL2 cross SL2.
Maybe. We didn't look too much at that, actually, but maybe, yeah. Although, I mean, it should sort of, I mean, you have both factors, so.
So the groups can be, not factor. Right.
Yeah, yeah. But anyway, so now we've been looking at the case of SL3. And so we would like to define, we just say the conjecture. The conjecture is that given a generic spectral curve phi dot, there will be a universal map to what we call a pre-building. So a pre-building is supposed to be something which looks like a sort of a piece inside a building.
Pre-war building?
Supposed to.
Such that with with the differential dHb equal real part of phi, such that for any locally harmonic map H, so with dH equals real part of phi. So we're saying, okay, let's suppose we know the differential, right? In our WKB problem, we started with a spectral curve, so we know what the differential is. Now we have now we're down to the point where you have a map to a building that has that differential. Now the question is, can we classify maps to buildings that have that differential? Sort of integrate the map, basically. So we say the statement we would like to get is just the same statement as the way I made it for the trees here, which is that there should be a map to. It turns out when you look at it, asking for the map to the full building, you can maybe ask for it. It's not going to be universal. It might be versal, but maybe that's not exactly the right thing to do. So the conjecture is that there's going to be a map to this pre-building thing. So for any locally harmonic map, there exists a unique factorization. F.
I forgot, is phi essentially the matrix that we're integrating?
No, this phi is the matrix.
Okay. It's finding a differential equation.
This phi, this square phi dot is the eigenforms of the matrix.
Oh, there's a dot there?
Yeah, there's a dot. This. Okay.
Okay.
So I mean, different matrices will be considered the same if they have the same spectral curve. Basically. Now we would hope that, and this is again for a generic spectral curve phi, that this F guy should be a physical isometry. So then the corollary will be that U omega Q is always equal to the same exponent UPQ. So that this limit actually exists. And that it's equal to the distance in this pre-building from HB of P to HB of G. So now I'd like to just discuss an example, which is kind of the only example that we've really understood fully here. In fact, now we've understood it in two different ways. So we wrote a first preprint last year, and now a second preprint just a couple weeks ago, re-looking at this example in a different way. So now we understand this example pretty well. This was an example which was mentioned, I think, by Guyotto and Neitzke as perhaps being the first example where their phenomenon of collision of spectral network curves actually showed up. So this is the example that I wrote down earlier. So
this conjecture says there's some structure for the general situation.
it says there's a structure for the general situation, yeah.
But what is the structure?
The structure is that there's a map to a pre-building. So a pre-building is like a building, except not really all that infinite. I mean, we don't have like an infinite bunch of many stuff.
Oh, there's actual
You'll see in the example here. Okay. So let's just, I wrote down this example previously because it was the example I wanted to talk about. This was occurred in that paper by Brook, Evans, and Rogers. So we have our spectral curve, which looks something like that. And we have these two ramification points. Okay. Now, if we draw inside in X, which is equal to C here, we make the following drawing. So this is going to be a drawing of the Gaiotto-Morexky spectral network. And what happens is we have two collision curves here. So at a branch point, there's naturally two of the three values of the function which come together at the branch point. As you go around the branch point, those two interchange basically. Okay. So this is a real part of phi I. Let's call it phi j minus phi k equals 0. This is a branch point for jk. This guy is going to be a real part of phi I minus phi j equals 0. These curves. So when you have a branch point, out of that branch point, you get what looks like the usual picture for the foliation associated to a quadratic differential. Because near that branch point, the spectral curve here just looks like a quadratic differential. But then these two guys can go out here, and this is what Gaiotto-Morexky sort of discovered. They can go out here and actually collide. So, and there's an ordering here. So this is I, J.
This is a picture where in C2?
This is a picture in C, in the complex plane.
C. Oh, X.
The X plane.
In X. Oh.
That's the X coordinate. The singular affiliation lines coming out of here and coming out of here can actually collide together and create an IK line. So this is real part phi I minus phi k equals 0. Okay. So this is Gaiotto-Morexky's spectral networks picture. And in their papers, they have lots of much more complicated pictures where you can have a zillion different foliation lines which all collide and do fun stuff and everything.
Why? Because they're using different examples?
I mean, as soon as you take a more complicated equation, of course, then you might have like a lot of branch points and everything. Even for the case of SL3. Now, let me just add in another thing, which is called the caustic. Because if you think about it a little bit, there's actually three foliations which we're looking at here. There's the important foliations are these three guys here. And a caustic is the place where these foliations are all tangent. And when the foliations are tangent, then points on opposite sides of the caustic have to get identified under the harmonic map. So remember I said that the harmonic map was given by this equation. And I said it wasn't supposed to fold things. It actually does fold the caustic. It is folding caustic, but that's allowable because that's given by the differential. That's a harmonic map. That's just, any linear map whose differential is given by these three differentials has to automatically fold. So now I have my picture. It's a little late here, but so point is that that's this guy. That was this picture here, which is a little smaller. Okay, that's the picture on the board. Now, if you look at that, if we use these if we use these foliation lines to define coordinates, that gives you a sort of a flat metric on the thing. And
sort of
flat metric, except on the caustic line. And this is what that flat metric looks like. Okay. Now, what happens is that these regions, such as I've drawn here and sort of somewhat big, have to get folded along the caustic. Okay. So now here's our process. So now we have a process, we have sort of a conjectural process to construct this guy. And I'll just illustrate the process with this example. So the process goes like this. You take this guy and you first notice that these pieces have to get pinched together. Okay. So there are some pieces along the caustic that have to get pinched together. By this map, yeah. So remember, we're trying to construct some kind of free building. The basic property of a pre-building is that it's supposed to be non-positively curved. Now, when we pinch together guys like that, we create a picture like this, basically. That's this is this space, but where
Oh,
What?
you stop when you get to the corner.
Well, I actually added some extra stuff so that we have a nice building-like thing. But you're going to stop when you get to here, exactly, yeah. But before we stop, so now we've just pinched together this, this, and this, right?
Yeah.
So now there's only one sheet of paper here, here, and here, but now here we still have two sheets of paper. And at those points, it looks like this, basically.
Oh, the other way.
At these points, right, this is just a bigger picture of this parallelogram here, for example. But we have the front sheet and the back sheet. But that's a positively curved point, right? There's only 240 degrees here. So this has to get pinched together when we go into a building. The only problem with this whole situation is that there's two ways of pinching this together. It can be pinched together like that, or even like that. So there's a question about how to control the information of who needs to get pinched together. Okay. We call that scaffolding. So scaffolding is an information of who has to get pinched together. Well, it turns out that on the Riemann surface, yeah. So part of our deal for the Riemann surface was that on the Riemann surface itself, we weren't supposed to fold a point in here that came from the Riemann surface. Right, a point here that came from a piece sort of came from just some point down here, basically. Right. So that's not allowed to get folded. On the other hand, these edges here, they're only there because we pinched together a front sheet and a back sheet. So there's nothing telling us that those aren't allowed to be folded. So that tells us which of the two possible directions needs to be folded. Then we do that once again when we get to this picture. So we do that, and then we also cut out these pieces, throw them away.
Why are you allowed to?
Well, we're going to put them back later.
Okay.
We cut them out. We get to another situation of the same situation with a fourfold point here that needs to get squished together. Then cut that stuff out, and then after we pinch the stuff together and then thrown away the stuff that got pinched, we get down to a picture like this, which is negatively curved. Okay. So now this is sort of the core of our pre-building. How to get back to building? We should just add in the stuff.
Image of the map.
Yeah, we should just add in the stuff that we cut out, which is something like that. Okay. So now we have a picture of the map from our original Riemann surface here into something which looks like this negatively curved two-sheeted thing, plus just a single sheet here, basically. And this is now valid as a pre-building, which is to say we can now start adding other stuff, a lot of other sectors, to make this into a building. Okay. So that's our conjectural construction. Now, why is it conjectural? It's basically because in this simple example, we could maintain the information of who gets folded and who doesn't get folded. So the conjecture is that under a genericity hypothesis, that you can actually continue to maintain that information of who gets folded and who doesn't get folded to decide. I mean, it's not sort of strange, but here we just are going to have a potential problem where we might not know. I mean, in a bad case, you might get down to a situation where you just don't have a canonical.
Very good. A double fold, yeah, that one.
Doesn't look too good
Do you
either.
mind that?
But,
Do you mind that?
well, I mean, you'd like to rule it out, or you'd like to at least know if it's supposed to happen or not supposed to happen, basically. So you'd like your scaffolding to tell you at each stage, are you supposed to be folding or not folding, basically? Because if you get down to a place, I mean, imagine you get to a situation where you just don't know which one might work. Then you wouldn't have a universal map anymore. You might have two possible different maps here. And then a given map to a building might be one or the other of those maps. And you just wouldn't know which of them they are. So our conjecture is that, more precisely, the conjecture is that if there's no what Guyotto and Morexky called BPS states, or sort of generalized saddle connections, then that's the genericity condition that you need here to make this work. Anyway, so I'll stop here.
How do you use it to get back to the original question of estimating the structure?
Well, then, once we have the map to the pre-building, at least, I mean, if the conjecture works, but for example, in this case, we can see. So that tells us the map to the pre-building looks like that, okay? So it means that in terms of this map, we just have to pinch together all the stuff I drew here. Okay. So that tells you, for example, that if you take, and now the distance you have to use the pencil distance, but you can think of that as basically being just
So
the
that's the
distance.
same exponent, those 2 points.
Those 2 points, the exponent to go from here to here is 0. Okay. Or the exponent, for example, to go from a point here to a point here is obtained by going up to here and then from here to here. Basically. You just go I mean, to go from down here to over here, you go up to here, over and down this way. Whereas you just couldn't see that in terms of the differential equation. I mean, in terms of the differential equation, if you try to numerically integrate your differential equation along any, you can choose whatever path you want. There's going to be no path in here where you could numerically integrate your differential equation and get that exponent. It tells you that if you're like having a computer and you like to numerically integrate your differential equation by dividing your path up into a zillion little segments and so on, you're just automatically going to get the wrong answer. That's new to the SL3 case. In the generic SL2 case, there always will be a path which allows you to get the right exponent. So starting from SL3 in higher ranks, there's just this phenomenon where points are actually closer together than they look like they might
Because
be.
of the flats.
Yeah, and it's because of the fact that you have a building and the negative Rayleigh curve property of the building and stuff like that.
So the setting of the discussion, I mean, rather than saying you were just working on C or on the upper half plane, you were implicitly saying something that you're working on the universal cover of some Riemann surface.
Yeah.
Is there an equivariant side of the story that you haven't told us where?
Well, I think so. I mean, as I said, the problem is this is a conjecture rather than a theorem. So, if we could show that this really existed and was unique, then if there was a group action, then that would have to act on here, basically. The case of a universal cover, I mean, the case I drew here is a really pretty simple case. So if you know something about quadratic differentials, you know that even for foliations defined by quadratic differentials on Riemann surfaces, then you go to the universal cover of the Riemann surface, you get a lot of problems where, like, I mean, on the Riemann surface itself, a leaf might sort of be dense or something like that. And here it's the same. I mean, even up here, these spectral networks might just be dense because you might sort of go out far away and then collide some stuff, and then that might send in a new, I mean, it's even worse than the case of foliation. In foliation, they all go in the same direction. Here we have 3 different foliations, so they could just sort of go all over the place and then collide with each other and then have new ones. So, I mean, a priori, if you sort of go far out and then back, you might have just a zillion collisions all over the place. So it's a little bit not, I mean, in an example like this where we just made up our example, and the collision guys sort of go far away and don't come back and on us later, you might say, then you can sort of geometrically see what's going on. So to make this actually work, in this case where you have a compact Riemann surface, and you'd like to then have an equivariance is on, that might be somewhat non-trivial, to say the least.
Is there a family statement where you vary the curve?
Well, yeah, so that's, I mean, that gets to this question about the relationship between, with this and all these things about stability conditions and stuff like that. So, in principle, you would like to vary the curve plus the spectral curve phi. But you have the Riemann surface, for example, and its spectral covering. And you'd like to look at the space of those guys. And so, roughly speaking, the idea is that that space maybe would be divided up into chambers, where the crossing, there's going to be some walls between those chambers, and crossing over those walls is going to happen when these VPS states, the combinatorics of these collisions, sort of changes. I mean, that's kind of the philosophy expounded by Morexky and Brook and Smith, and I'm just sort of reporting that philosophy. But so the philosophy would be that if we look at that, we should look at sort of the full, as you say, the full moduli space of Riemann surfaces plus spectral curves and everything, and try to understand, you know, combinatorially how things are changing. That was kind of the reason why we were motivated to look at this type of a question for those stability condition questions, which is that maybe this pre-building is sort of a good combinatorial object, which you can then study how it varies. We don't actually know how it varies, but I think that's one of the next steps.
What is the math idea for these things you're calling VPS states? What's the math structure?
The math structure is that, so here I drew one which doesn't have one, but, so in the case of trees, what's just called a saddle connection is when you have 2 different branch points they're connected by a leaf of the foliation, right? If we modify, as you said, for example, the differential or something like that, on one side of the saddle connection, it might look like that.
Oh, saddle connection.
And on the other side of the saddle connection, it might look like this. And sort of in between these two pictures, we have a somewhat degenerate picture where the two branch points are on the same leaf. So now, what Guyotto and Morexky say here, and this is sort of the more interesting part, but we're sort of throwing that out by our genericity condition. But sort of the interesting things start happening here when you have
So this is a
saddle
wall
connection.
crossing thing, or?
Well, there's going to be a wall crossing when you go from here to here to here, basically. This is going to be the wall. But in the higher rank case, you can have you can have collisions here, right? We might have had an IJ and then a JK. They might have collided and created an IK guy. Then this guy himself might have collided, you know, with a JI or something like that. Then this guy might have been a branch point itself. For example, this would be a JK. So, for example, you could have 1, 2, 3, 4 branch points, creating a spectral network. Probably didn't draw this too well, but.
What does this have to do with the higher rank? Because you have more than one. What's changed?
Well, this doesn't happen in the rank 2 case, in the SL2 case.
The spaghetti differential doesn't do that?
Well, there's no way of colliding because, see, the collision has to do with assigning indices.
Oh. You need to do more indices.
It has to do with assigning indices. So here we have an index ij, and here we have an index jk, and when we collide, we get index ik. So if you only have 2 indices I or 1 and 2, then that doesn't happen.
Okay.
But I mean, this still happens, but the more general collision thing doesn't happen. So this, I guess, is a picture of a BPS state where
For the indices, there's some interaction.
the indices interact in a certain way.
I've been hearing this for years.
Yeah.
Very similitude of reality.
Well, I don't know how the physics work there. Then there's a whole story about Calabi threefolds and stuff like that, which I, again, am definitely not an expert on. But where I mean, these indices, you can think of them as determining sheets inside the spectral curve. So basically, we have 2 sheets in the spectral curve here, then 2 other sheets in the spectral curve here, and when they meet, then we just get these 2 sheets in the spectral curve. So this whole picture is going to determine a loop on the spectral curve, actually.
So a lot of this wouldn't happen in SL2 cross SL2.
No, this collision phenomenon is not going to happen. No.
Even though the geometry is similar to the geometry of SL3, the symmetric spaces are kind of similar in some ways.
Mm-hmm. But part of what we're saying here is that when you have these collision points, that's actually corresponding in the building to a place where there's sort of a singularity in the building, basically. In some way, we don't have an extremely precise statement about that.
So this is actually closed geodesic on the spectral curve in the metric absolute value of y squared.
I guess so, if you say so.
So for you, the model for the BPS, this is not about this. It's just a model BPS state. For them, they're looking for closed geodesics on the spectral curve. There's some metric on the spectral curve, which is given by the absolute value of y squared. That's just
So you're saying that these are sort of approximations or something like that?
yeah.
Part of the problem is I don't understand anything about the physics point of view here, but
Actually, physics-wise, the natural question would be to map not the x space onto this tree, but actually the y space. So my question is, can you partially invert the map? Choose
Where's the X and the Y? Over there.
There's x and y.
why is the cotangent? Why is the momentum parameter? You might say the
So actually,
cotangent.
X is the parameter of the surface.
can you rotate the picture 90 degrees?
Well, in this case, you can rotate it. In fact, that's what
No,
Brook
this
said.
is a probably misleading example because your x dependence of phi was very simple.
X is the function of y here. So, and that's what Varros immediately said, oh, this is trivial because it's just the Fourier transform of a rank 1 system. But we're just using this as an example.
So if we
Understand
had
geometry.
experiment at least.
Yeah.
It would be not trivial.
It would just be, it would have been a little more difficult to make. I mean, we did we understood what was going on a lot due to computer pictures of of these spectral networks.
Because if you reverse the picture, then there is a probabilistic interpretation of the branch counsel features and things like that.
I don't know.
You know, when I was an undergraduate, I read E.T. Bell's book about mathematicians that Jacobi was trying to do this elliptic integral or something, and then his great invention was to inverse the function, and then suddenly all this stuff came out. So maybe he's
Yeah, I'm certainly.
No, I just know where this stuff comes from. So
because for where it comes from, you should look at the inverse function. Okay. Well, Jacobi.
Okay, good. That's a good tradition.